Okay, so in the last video, we got the fundamental theorem of calculus part 1 that basically said if we've got a continuous function of t that we're going to call our height function, and we define this related area function from a fixed starting point to a variable ending point, the definite integral of that height function, if we then take the derivative of that area function, we will get the height function, but we get it back at x. Okay. Now, that gives me a really strong geometric connection between this area function and this height function. Its significance is really this: antiderivatives of continuous functions exist. Okay. I can find a function that's an antiderivative of any continuous function. I can do that by creating an area function. So when we studied antiderivatives, we said, what's an antiderivative of cosine? And we said, oh, sine is, because if I take the derivative of sine, I'm going to get cosine. Well, let's suppose I had f of x equals sine squared x times the natural log of x all over e to the 2x. Okay. I cannot, off the top of my head, think of a function whose derivative is going to be that I could build the usual way by just using powers and trig functions and exponentials and logs and stuff like that. But I can find an antiderivative. An antiderivative would simply be the integral from, give me any fixed starting point that's in the domain of this function. So it would have to be a positive number in order to be in the domain. So let's just say 1. The integral from 1 to x of sine squared t natural log of t over e to the 2t dt is an antiderivative. Okay. So if I have a function, if I turn it into the height function and create a related area function, I've just created a function whose derivative is going to be that function. Okay. So it tells me that antiderivatives exist. Even if I might be hard-pressed to come up with a nice, neat formula for one, I can always come up with one by just creating an area function. Now, in practice, this isn't particularly user-friendly, so it's nicer when I can have something like cosine and say, oh, I recognize that that's the derivative of sine, so sine would be an antiderivative. But I can create antiderivatives by just using, creating an area function. All right, what I want to do now is practice using this fundamental theorem. So let's define a of x to be the integral from, let's say from 2 to x of the square root of t squared plus 5 times sine of t dt. So notice this is an area function. Okay. Excellent. Now, this looks like kind of a messy area function, but let's just evaluate this. So let's find the area function at 2. Let's find a prime at 2. Let's find a prime at pi over 2. And let's leave it at that. Let's find those things. So a of 2, I'm just plugging in 2 for x. So that would be the integral from 2 to 2 of the square root of t squared plus 5 times sine t dt. And I don't really care what the integrand is. Once my limits of integration are the same, that's going to be 0. Okay. If I look at a prime of 2, okay. Now, anytime I'm finding a derivative at a particular point, I need to remember that that's a two-step process. I want to first of all find the derivative formula, and then I can plug in that point. So a prime of x, we're looking at the derivative with respect to x of this area function. Okay, so we need a strategy. Step one, let's not panic. That looks atrocious. If I were to just throw that to you out of the blue, you would say, oh my goodness, no, I just can't do it. Okay. You need to recognize, though, that, oh, that looks like an area function. So it might be easier than it seems. So we can say initially, oh, that looks dreadful, but I'm not going to panic. I'm hoping this is easier than it looks. Step two, I'm going to check. Does this match an area function? So do I have a fixed lower limit of integration and a variable for my upper limit of integration, and then some function of t that I'm integrating with respect to t, just so this variable is not the same as that variable? Yes. Excellent. So this basically was my f of t. Derivative of area is height function. I'm just going to get f of x. So I'm going to get the square root of x squared plus 5 times sine of x. That is my formula for a prime. Now, that means that a prime of 2 is what I get if I plug in 2 for x. So let's see. 2 squared is 4, plus 5 is 9. Square root of 9 is 3 times sine of 2. And sine of 2 doesn't simplify particularly nicely, so we'll just leave that as sine of 2. Excellent. Okay. Now, if I want to evaluate a prime at pi over 2, I've already done the work of finding this formula. I'm just going to plug in pi over 2. So that would be the square root of, that's going to become pi squared over 4 plus 5 times sine of pi over 2, which is just 1. So I get the square root of pi squared over 4 plus 5. So that first step of not panicking is really crucial for using this part of the fundamental theorem of calculus. It's not as bad as it looks. Okay.